Welcome to the deep dive. Today we're digging into something absolutely central to the AI boom, but maybe not always fully understood. Nvidia's CUDA platform. Everyone knows Nvidia sells the GPUs, right? Those super expensive chips. But talk to anyone deep in AI development, and they'll often say the real power, the secret sauce, isn't just the hardware. It's this piece of software called CUDA.
That's exactly right. And our sources really hammer this home. CUDA is consistently called one of the most successful platform plays ever in computing, maybe the most successful. It's seen as the indispensable foundation for the whole AI revolution we're living through. And crucially, this wasn't an accident.
No luck involved.
Well, maybe some good timing, but mostly it was a deliberate, multi-decade strategy building this really deeply integrated software ecosystem. And that ecosystem, that's the competitive moat we're talking about. It's formidable.
Okay, so our mission today is to kind of cut through that complexity. We want to give you, our listener, the shortcut to understanding CDA's dominance. We'll break it down into, let's say, three main parts. First, how it all started, going from clever graphics workarounds to enabling this AI big bang.
Yeah.
Second, we'll look at the tech itself, the architecture, and how that creates what some people call a skill moat, makes it hard to switch. And finally, the huge software ecosystem around it, which might be the toughest barrier of all for competitors. Sound good?
Sounds perfect. Let's dive in. Right, so to really get why CUDA was such a big deal, you kind of have to picture the world before 2007. Our sources call it the GPGPU Dark Ages.
GPGPU meaning general purpose computing on GPU.
Oh, exactly. Using those chips, which were designed for graphics, for general math and science problems, it was technically possible back then.
By practical?
Not really. It was incredibly difficult. If you were, say, a scientist wanting to run a big simulation, you couldn't just write standard code.
You had to do what, sort of fool the graphics card?
Pretty much. You had to map your scientific data onto things like graphical textures and your algorithms. You had to write them as if they were pixel shaders or vertex shaders.
Wow, so you needed to be a graphics expert just to do parallel computing.
Basically, yeah. You needed deep knowledge of graphics APIs like OpenGL or Direct3D. This was a massive hurdle. It locked out almost everyone, scientists, engineers, who needed that parallel power but had no reason to learn graphics programming.
That sounds incredibly inefficient, like needing to understand internal combustion just to drive. So what changed? Where did the idea for CUDA come from?
Well, the initial spark, the blueprint, really came out of academia. There was this researcher, Ian Buck, who developed something called Brook. It was an extension to the C language to make data parallel programming easier. And Nvidia saw the potential. They realized, wait a second, this GPU isn't just for graphics. It's essentially a parallel supercomputer waiting to be unlocked.
And their CEO, Jensen Huang, was behind this.
Absolutely. In 2004, they made a huge strategic bet. They hired Ian Buck and committed serious resources to building this new software platform from the ground up.
And the core goal was accessibility. Make it easier for regular programmers.
Exactly. That was the key insight. Instead of forcing people to learn graphics APIs, they decided to extend familiar languages C and later C++A. This dramatically lowered the barrier to entry. They weren't targeting the few graphics wizards anymore. They were targeting the millions of C and C++ developers out there who could benefit from parallel processing.
Makes sense. Build it so they can come.
And they came. But the real explosion, the moment everything changed, was in 2012, the AlexNet inflection point.
Oh yeah, the ImageNet competition.
Right. A neural network called AlexNet just blew away the competition. Stunning victory. Achieved results nobody thought were possible at the time.
And the key hardware detail.
It was trained using two Nvidia GeForce GTX 580 GPUs. Consumer cards, basically. But critically, the team had written custom CUDA kernels to accelerate the training.
So that was proof positive.
That was the proof. The big bang for modern AI, you could say. It showed GPUs weren't just a bit faster. They were orders of magnitude more effective for deep learning than CPUs. And since CUDA was really the only mature, usable platform ready for that kind of workload, boom, it became the default choice almost overnight. That first mover advantage just kept compounding.
Okay, so that explains the strategy and the timing. Now let's get into the weeds a bit on the architecture. Why is it so fast? And what makes it, difficult enough to create this skill mode?
It really boils down to a fundamental difference in design philosophy. You've got CPUs versus GPUs. Think of a CTU as being latency optimized. It's like a master chef, highly skilled, focused on getting one single complex dish a task done as quickly as possible from start to finish, minimizing the time for that one thing.
Right. Fast sequential processing.
Exactly. Now, a GPU, and therefore C80A, is throughput optimized. It's not a single chef, it's a massive assembly line. Thousands of workers, maybe less skill individually, but all working in parallel on small parts of a huge job.
Like processing pixels or in AI, matrix math.
Precisely. CUD is essentially the management system, the foreman, for that giant assembly line. It's designed for problems you can break down into tons and tons of identical, independent calculations. Matrix multiplication is the classic example, fundamental to deep learning.
And the programming model reflects this. The CPU tells the GPU what to do.
Yep, it's a heterogeneous model. The CPU is the host. It sets things up, manages the overall flow. The GPU is the device doing the heavy parallel lifting.
And the specific function that runs on the GPU, that's the kernel.
That's the one. You write a function, you mark it with global in CUDA C++E, and that's your kernel. That's the code that gets executed by potentially millions of GPU threads in parallel.
Millions of threads sounds like chaos. How does CUDA manage that?
It uses a hierarchy. At the bottom, you have the individual thread, smallest unit. Threads are grouped into blocks.
And blocks are important because
Threads within the same block can cooperate. They can share data really quickly using a special type of on-chip memory called shared memory that's super fast.
Okay, threads and blocks make up.
The grid. The grid is just the entire collection of all the blocks launched for a specific kernel call. So you have grid blocks threads.
All right, that seems logical. But where does the difficulty, the skill moat come in? Is it just writing the kernel?
Writing a basic kernel isn't that hard, especially now. The real pain and the real performance gains come from optimization, and that often involves understanding the hardware execution model.
Which involves the warp.
Exactly. Inside the GPU hardware, threads are actually executed in groups of 32, called a warp. Think of it as the smallest manageable unit for the hardware scheduler.
And the catch is?
The catch is all 32 threads in a warp are supposed to execute the exact same instruction at the same time. That's where the efficiency comes from. But what happens if your code has, say, an if-else statement, and based on the data, maybe 16 threads in a warp need to take the if path, and the other 16 need to take the else path?
Uh-oh, they're not executing the same instruction anymore.
Bingo. That's called control divergence, and the hardware has to handle it somehow.
Does it just slow down?
It effectively serializes that part. The hardware will run the if path for the first 16 threads, while the other 16 wait. Then it runs the else path for the second 16 threads, while the first 16 wait.
So you completely lose the parallel benefit for that section.
You got it. It negates the benefit of parallelism. Avoiding control divergence, or structuring your code and data to minimize it, is a major part of high-performance CUD programming.
Okay, so control divergence is one hurdle. What else builds this skill mode?
The other huge factor is managing the memory hierarchy. You've got super fast registers right on the chip, then the slightly slower but still fast shared memory within a block.
And then the main GPU memory, the VRAM, which is much slower.
Right, that's global memory. Accessing global memory is orders of magnitude slower than registers or shared memory. So a massive part of optimizing CUD code is about minimizing those slow global memory accesses. You want to load data into shared memory once, have the threads in the block process it extensively, and only write results back out to global memory when absolutely necessary. Mastering this memory management is complex.
So organizations invest heavily in training developers to handle warp divergence and memory optimization.
And once they have that expertise, switching to a different platform means potentially throwing away that investment and starting over. That's a powerful disincentive. That's the skill moat.
But wait, you said earlier Nvidia wanted accessibility. If optimizing is this hard, how do beginners even start? Didn't they add features to help?
Good point. Yes, they absolutely did. That's part of the brilliance, maybe. They introduced features like unified memory, starting around CUA 6.0. Unified memory basically creates a single memory pool accessible by both the CPU and GPU. The CUDA driver and runtime handle migrating the data back and forth automatically as needed.
So beginners don't need to manually copy data between the host and device all the time.
Often no. It significantly lowers the initial barrier. You can get code up and running much faster without worrying about explicit cuDNN calls everywhere.
Clever. So it's easy to get started, which draws people in.
But to get really high performance, especially for complex problems, you still need to dive deep into managing warps and memory manually. The simplicity gets you hooked. The complexity keeps your experts invested.
Okay, so we have the hardware, the core programming model with its skill mode. But you mentioned earlier that the real strategic advantage, the truly inescapable part, is the ecosystem built around CHEC++ Plain.
Absolutely. The language itself is just the entry point. The billions of dollars, the decades of engineering effort have gone into the software, the tools, the libraries that surround it. That's the true competitive moat.
Let's break it down. What's the foundational layer of this ecosystem?
That would be the CUDA toolkit. This is what developers download. It includes the essential compiler, NVCC. And NVCC is interesting because it usually compiles your CUDA C++ code not directly to machine code for a specific GPU, but to an intermediate language called PTX, parallel thread execution.
Why the intermediate step?
Crucial for compatibility. We'll touch on that later. But the toolkit also includes incredibly mature developer tools. The star here is the Nvidia Nsight suite.
Tools for debugging and profiling.
Yes, but really sophisticated ones. Nsight lets you dive incredibly deep. You can see exactly which lines of your kernel code are causing warp divergence, pinpoint memory access bottlenecks, visualize execution flow. It gives developers amazing visibility into performance issues. That level of tooling maturity is hard for competitors to match.
Okay, so the toolkit is layer 1. What's layer 2? You mentioned libraries.
Yes, and this is arguably the most critical layer for most users today. The CDAX libraries. Think of these as highly optimized, pre-built functions for common computational tasks. Most AI developers nowadays aren't actually writing their own low-level CAD kernels for things like matrix multiplication or convolutions. Why would they? Nvidia has teams of engineers who have already done it and optimized it to the absolute limit for every GPU architecture.
They're just calling these pre-made library functions from Python or C++.
Yeah. Exactly. They leverage these computational primitives, and there are a few key ones, especially for AI.
Like what?
The most important one is cuDNN, the CUDA Deep Neural Network Library. It provides GPU-accelerated building blocks for deep learning. Convolutions, pooling, activation functions, you name it.
And all the major frameworks use this.
Every single one. PyTorch, TensorFlow, JAX. They all rely heavily on cuDNN under the hood. Then there's cuBlaze for super fast linear algebra basic matrix operations, fundamental for almost all scientific computing and machine learning. And for really big jobs, training models across many GPUs, maybe even multiple machines, there's NCCL, the NVIDIA Collective Communications Library. It handles efficiently shuffling data between all those GPUs, essential for large-scale distributed training.
Okay, so developers use frameworks like PyTorch, which in turn use cuDNN, cuBlaze, and CCL, all built on CDA. It's layers upon layers.
Precisely. And this leads to what our sources call the virtuous cycle. It's incredibly powerful for NVIDIA.
How does that cycle work?
NVIDIA engineers hand-tune these libraries, cuDNN, cuBlaze, etc., for every single new GPU they release. They optimize them down to the metal for that specific architecture. So what happens? A developer using PyTorch or TensorFlow upgrades their NVIDIA GPU to the latest model, they update their CUDA toolkit and drivers, and suddenly their existing AI training code without them changing a single line.
Just runs faster.
Often significantly faster. They get a free performance boost just by buying the new hardware and updating the software stack. That promise consistent performance improvements without rewriting your application is incredibly sticky. It makes staying within the NVIDIA ecosystem the path of least resistance.
Wow, that's a deep moat. And this integration drives adoption everywhere.
Everywhere. Obviously in AI research and training massive models like LLMs, but also huge in high-performance computing, scientific domains like molecular dynamics, climate modeling used in major national labs, and increasingly in enterprise. The sources mention companies like Lowe's using GPU acceleration for optimizing their supply chain, or Pinterest using it for visual search. They might be using higher-level NVIDIA tools like the Rapid suite for data analytics, but underneath it all,
It's CUAX running the show.
it's all CUDA all the way down.
Okay, given this stranglehold, this incredibly deep moat built over decades, it's not surprising the rest of the industry feels a bit constrained.
Oh, definitely. CUDA is proprietary. It only runs on NVIDIA hardware. That single vendor dependency makes a lot of companies and researchers nervous, so there's a huge constant desire for open alternatives.
And the main contender trying to offer that alternative today is AMD with its ROCm platform.
That's right. ROCm Radeon Open Compute Platform. It's AMD's open source software stack for GPU computing, and their key piece for trying to woo CUDA developers is HIP. Heterogeneous Compute Interface for Portability. It's basically a C++ API that's deliberately designed to look and feel almost exactly like CUDA C++ key. The function names, the concepts, they mirror CUDA very closely.
To make it easy for CUDA programmers to switch.
That's the idea. They even provide a tool called HIPIY. Its job is to automatically translate existing CUDA source code into HIP source code.
Okay, wait. If they can auto-translate the code, doesn't that kind of break the skill moat we talked about? If your code can just be ported automatically.
It's not quite that simple. HIPIY can handle a lot of the syntactic translation, which is a good start. It lowers the initial porting effort. But translating the syntax isn't the same as translating the performance. Remember all that Nsight tooling we talked about? The deep profiling, debugging, and the decades of optimization baked into cuDNN and cuBLAS for every Nvidia chip.
Right. ROCm has its own libraries, but they're not as mature or as broadly optimized.
Exactly. ROCm has improved tremendously, especially recently. And in certain specific workloads, particularly things like large language model inference, which can be memory-bound, ROCm performance on AMD hardware can be very competitive. But across the board, especially in training, and critically, in the maturity and breadth of the surrounding ecosystem, the libraries, the developer tools for performance tuning it still generally lags behind COD and Nsight. Debugging a tricky performance issue on ROCm can often be a more painful, manual process compared to the visibility Nsight gives you.
So the code might port, but getting to run well and debugging it efficiently is still harder.
Often, yes. That ecosystem maturity is NVIDIA's huge advantage.
But it wasn't always just AMD, though. There was another big push for an open standard years ago, right? OpenCL. What happened there?
OpenCL, yeah. That was the industry's big hope for a truly cross-vendor standard back in the late 2000s. The goal was noble. Write code once, run it on GPUs, CPUs, FPGAs from any vendor.
Sounds great. Why didn't it take off against COD?
Several reasons. It was designed by a committee, which made its evolution very slow and often resulted in compromises that satisfied no one perfectly. Worse, the implementations varied wildly between vendors. Code optimized for one vendor's OpenCL might run poorly or even have bugs on another's. This lack of consistency killed developer confidence. Someone famously described writing portable, high-performance OpenCL as being as comfortable as hugging a cactus.
Ouch. Not a great developer experience.
Not at all. And crucially, OpenCL lacked that rich ecosystem of high-level, vendor-tuned libraries like cuDNN. You often had to write complex kernels yourself, which brought back the difficulty CUK was designed to solve. So while it still exists and is used in some niches, it never really challenged CUDA's dominance, especially in AI.
So if competitors like AMD are still fighting to catch up on the programming model and libraries layer, what's Nvidia doing? Just defending CD, C++?
Oh, no, they're not sitting still. They're doing something very clever. They're actively expanding the moat by moving up the stack.
Moving up. What do you mean?
They're shifting the battleground away from just the low-level programming model, CUDA, C++, spell-it libraries, where competitors are trying to gain ground. They're increasingly offering higher-level integrated solutions.
Can you give an example?
Sure. A prime example is their recent push with NVIDIA Inference Microservices, or NIMs. These aren't just libraries. They're prepackaged, containerized AI models ready to deploy. A NIM might contain an optimized large language model, complete with the inference server software, all tuned to run efficiently on NVIDIA GPUs. It abstracts away almost all the underlying CUDA complexity.
So an enterprise doesn't even need deep CUDA expertise to deploy that model.
Exactly. NVIDIA is essentially turning CUDA into something more like an operating system for AI. They provide the whole stack, from silicon up to deployable application containers. This shifts the decision for businesses. It becomes less about which low-level programming language do we bet on, and more about which platform NVIDIA's integrated NIMs or trying to piece together alternatives gives us the fastest, most reliable path to deploying AI. By making their own high-level solution the easiest path, they reinforce their dominance at a whole new level. #outro.
Okay, so wrapping this up, if we look at why CUDA has been so dominant for so long, it seems like it's not just one thing, but four interconnected pillars. You've got the superior hardware, obviously critical, then the CUDA X software stack, those libraries like cuDNN, meticulously optimized over years.
Right.
Third, the deep integration with all the AI frameworks everyone uses. And finally, just the sheer momentum, the massive developer mindshare and community support, that network effect.
That sums it up really well, and it brings us back to something we touched on earlier, this interesting portability paradox.
Paradox, how so?
Well, CUDA code itself isn't portable, right? It locks you into NVIDIA hardware. That's the vendor lock-in problem. But NVIDIA goes to great lengths to guarantee cross-generation portability within their ecosystem.
Using that PTX intermediate code.
Exactly. Remember, NVCC compiles to PTX. That PTX code isn't specific to one GPU generation. Then, when you run your application, the Nvidia driver has a just-in-time JIT compiler. That JIT compiler takes the PTX and compiles it down to the specific machine code for the actual Nvidia GPU you're running on at that moment.
So code compiled years ago on an older version of CDA can still run, and potentially run faster, on brand new Nvidia GPUs without the developer needing to recompile the original source.
Precisely. That forward compatibility, that stability guarantee, is hugely important for enterprises making big, long-term bets on the platform. It mitigates the risk of vendor lock-in somewhat by ensuring your investment continues to work on future hardware.
That's a really key point. It's lock-in, but it's stable lock-in, in a way.
You could put it that way. It really defines the current landscape. The future seems set to be this ongoing tension. NVIDIA's powerful, vertically integrated, high-performance but proprietary platform versus the constant push from the rest of the industry for open standards and alternatives like ROCm. Maybe the provocative thought to leave you, the listener, with is this. After 2 decades of focused, single-company engineering driving CUDA forward, can a more fragmented, open-source, committee-driven approach ever truly replicate that level of performance, integration, and ecosystem maturity?
A challenging question indeed. Can collaboration catch up to that kind of sustained, singular vision? Something to think about.